if you would recall, last week we had this surface area function, which was the surface area of a cylinder with a fixed volume of 250. In that case, it was milliliters or cubic centimeters, which means that the radius must be being measured in centimeters. And our goal was to minimize the function, and we used calculus to do it. But what I want to do today is think about the graph of this function, because it's kind of a strange graph. Okay. So what I first want to do is get rid of some of the noise in this function. There's like this 2 pi coefficient and then this 500 coefficient. That makes the graph look very strange. So if we switch over to our graphing calculator, if we just try to graph this function, 2 pi times r squared, oops, let's go x squared so it knows it's a variable, plus 500 over x. Well, that's not very helpful. It's that green line. And it's like, well, that's not very helpful. We have to zoom way out. See, even though stuff is happening in this problem for positive values of r, that's the only part we care about. We also have to get our vertical scale in mind, because this is only going up to 20, and our surface area was like 250 or 220 or something like that. So we've got to go way up here, and we start losing some of our detail. The point that we were looking for was way up here. 3.414. I can't remember what the exact value of this was. But this graph is a little bit messed up. The scale is all weird. So what we're going to do is we're going to get rid of some of this noise. First of all, this 500 is providing a lot of noise. This is also not helpful. This 2 pi is also kind of noisy. So here is a little bit better representation of what we're looking at. Any questions? Just want to, let's eliminate some of the noise. So I just want to look at x squared plus 1 over x. Here's what we want to look at when we look at this x squared plus 1 over x. Here's what we want to look at with this x squared plus 1 over x. Depending on the values of x, one of these terms is way more important than the other to the value of the function. There's x squared plus 1 over x. Depending on the value of x, one of these terms will be way more important. For large values of x, x squared is going to be large squared. That's going to be more important than 1 over large, because 1 over large is small. For large values of x, x squared is the important term. 1 over x becomes less important as x gets larger. For large values of x, x squared is the important term. For large values of x, the x squared is the most important term. We don't even have to get x very large now that I've cut out a lot of this noise. X doesn't even have to be very large to see this happen. Even if x is only 10, which is not large at all, the x squared is a 100, and the 1 over x is 1/10. The x squared is giving us 100. The x squared is giving us 1/10. This is only exasperated further for larger values of x? For x equals 100, which is still not a very large number when we're thinking about what happens when x goes to infinity, we've got 100 squared plus 1 over 100. So even just going out a factor of 10, our x squared term is now at a 10 to the fourth. And our 1 over x term is even smaller at 0.01. Even at this point where x is only 100, it's pennies compared to $10,000. So for large values of x, x squared wins. It's the most important part of the function. But for small values of x squared is less important, and 1 over x starts to win. It makes sense. The limit as x goes to infinity of x squared is infinity. The limit as x goes to infinity of 1 over x is 0. So this actually perfectly sensible. We have the language of limits. The limit as x goes to infinity of x squared goes to infinity. And the limit as x goes to infinity of 1 over x becomes less important. Oh, I can actually say equals 0 because it's 0. But if we start thinking about values of x that are close to 0, the role gets reversed. For values of x close to 0, one over x is the most important term. There's only two. I don't know why I bothered saying most important. It's like saying the plural of priorities. You can't have plural priorities. You can have one. You get one priority. You get a priority, that's the thing that you have to deal with now. Everything else is not a priority because you're dealing with the priority. That's what pri in the priority means. It's the most important thing. You can't have 12 most important things. You know what I mean? So when people say, get your priorities straight, I'm like, oh, pick one. Anyway, that's just a language thing. This is because not about my complaints about English, but my complaints come from being a mathematician where the words are supposed to mean something. So I don't know why I said most important term. There's only two. If one is important, the other one is not important. So for values of x that are close to 0, 1 over x is going to be the important term. So for x equals, say, 1/10, that's not even that close to 0. I've got 0.1 squared plus 1 over 0.1. The 0.1 squared is 0.01, 1/100. But the 1 over 1/10 is a 10. So for values of x that are close to 0, it's 1 over x that matters. Go from 0.1 down to 0.01, and all of a sudden our x squared is only contributing 1/10,000th, while our 1 over x is contributing 100. the closer we get to 0, the more significant the 1 over x term becomes. The closer we get to 0, the less significant x squared becomes. So let's take a look at our graph again. Let's switch over to our graph of x squared plus 1 over x. So here in green is our graph of x squared plus 1 over x. And we can see what's going on a little bit. We see this vertical asymptote at 0. So the x squared plus 1 over x has a vertical asymptote at 0. That's a point where x squared plus 1 over x is undefined. And in this case, it's undefined in the worst possible way. We got 1 divided by 0 for positive values of x. It's going towards infinity. For negative values of x, it's going towards negative infinity. We can't even pick an infinity to say we're approaching. That limit super doesn't exist. But the further we go away, we can see that asymptote becoming less important. And the graph starts to look more like the x squared. So if I put in the graph of the x squared, we can see that what's happening. The graph is trying to look like x squared, and when we're far away from 0, the graph is very close to looking like x squared. But when we are close to 0, the asymptote wins. So we can see this combination of x squared and the 1 over x. For large values of x, it's kind of like the parabola is acting as a long-run asymptote for this function. As x goes to infinity, this function looks more like x squared. As x is going to plus or minus infinity, the x squared is just going to look like x squared, and the 1 over x is going to look like 0. As x goes to 0, the graph looks like 1 over x, which goes to infinity, or negative. This is not correct notation. This is just us trying to summarize the idea using our language of limits. Any questions? We can think of the graph x squared plus 1 over x as the graph trying to look like x squared and being interrupted by this vertical asymptote. We could use this to better understand behavior around asymptotes. But for the purposes of the problem, we can now see, and once we understand what an x squared plus 1 over x graph is going to look like, we have a better understanding of why we know we're going to find a local minimum. We're going to try to see this graph that looks like a parabola, but we're going to have this vertical asymptote interrupt at 0. And that's going to take this parabola, and as we get closer to 0, whoops, from your perspective, yeah, from your side, as it gets close to 0, it's going to head off towards infinity. And then coming from the other side, the graph is trying to look like the parabola, but as we get closer to 0, that term becomes more and more effective, and it just bends the graph all the way down towards negative infinity. Any questions? That's the way we want to think about this kind of graph. X squared plus 1 over x. That 1 over x puts a vertical asymptote at 0. So if I start moving this around, first of all, I'm going to widen my graph. So I'm going to widen my graph because here's what I want to do now. I want to take that 1 over x and I'm going to move the asymptote back and forth. So if I put 1 over x plus 2, notice that I'm still making a graph that tries to look like the parabola, but now we're going to have a vertical asymptote at 1 or at x equals 2. Will that let me do it? No, sorry, negative 2. Dots are kind of cool, but I think the dashes are better. So there we see that the graph is trying to look like the parabola x, well, 1/10 x squared, because I need it wider. But that 1 over x minus c is moving around this vertical asymptote. It's interrupting the graph. As long as we're kind of far away from c, the graph gets to settle down and look like the 1/10 x squared. But close to c, the asymptote wins. So notice that what's going on with this asymptote.
No, 問號有幾多錢啊？我知啊，大概係要問啊，你點解？我爸爸嗰個，爸爸付錢。好，我都係諗問爸爸，冇問死。爸爸付錢嘅。佢話如果你個 income，或如果你個 asset 係多啲定0蚊咧，你係要講幾多咁問法 ？Last year 唔使咁啊，我諗而家佢要問。
There we go. I can put C in motion again. Notice that the graph is following the graph of 1 over x minus c. So from the left side, it's going down towards negative infinity, and then from the right side, it's going up towards positive infinity. So let's change what's going on with this x minus c. Note that if I square this, then both sides are going to go towards positive infinity, because I'm going to take the 1 over a small negative number that gets squared, becomes an even smaller positive number, smaller in value, but positive. So 1 over x minus c squared, or 1 over the square of the difference of x and c, is always going to be positive. So let's see what happens if I square the x minus c in our square graph. Now it's mimicking that behavior around the vertical asymptote, and both sides are going the same towards the same infinity. And moving it back and forth does the same stuff. Closer we are to the value of c, where the vertical asymptote is, the more the graph has to pull up towards infinity. The further away from c that we go, the more the graph gets to look like its polynomial term, 1/10 x squared. Any questions? And now the dance is back and dancing back and forth. It's important that you see that both sides go towards positive infinity and phrase it that way. because we can't say both sides go up. Because people will be like, well, up what? Up the, and then you can't say the rest. This, by the way, if you took pre-calculus in high school, why you might not have talked about rational functions and graphs of rational functions. Because we know that when the denominator is equal to 0, you either get a hole in the graph or an asymptote. And you cannot talk to a high school class about graph holes and asymptote. It's not going to work. Once you say that, the class is over. Ask me how I know. I had a high school class and it was full of graph holes. It's different. It was an all boys school and they were all teenage boys. And so therefore a bunch of savages. Well, at one point I was a student. Any questions? Anybody being hypnotized by our graph going back and forth? I want you to focus very carefully on the vertical asymptote as it slides gently back and forth. Showing the graph. I want you to focus. Maybe it's making a little wave sound. Now, what you want to do is take out the That's like you. I don't have Dang it. I'm just kidding. I wouldn't bother stealing from you all. I just assume that students don't have money, so there's no point in stealing from you. If I really wanted to steal your money, I would convince you that college is important and ask you to go into debt to, oh, I should have been the banking side, not the teaching side. And I'm just a pawn in this whole scam. It's terrible. Any questions? What's cool is that the even, or whether this is even or odd, the parity. If I go back to an odd, since odd powers respect negatives, notice that my negative side is going towards negative infinity again. Also notice that if I multiply by -1, that'll do. Negatives become positives, positives become negative. And if I just change this to, let's say, minus, then that's the same thing. Then I can put it back into motion and we can hypnotize again. Stop, hammer time. Any questions? So when we have like these very simple rational functions where we can separate out a polynomial term and then the rational term. It's like the rational term with the denominators, the variable denominators. That's what's giving us our vertical asymptotes or maybe holes in the graph. And it's the polynomial term that's determining the long run shape of the graph. So if I go up here, okay, this one could go, and I change my, let's just make it like 2x minus 3. Oops, minus 3. And I change my polynomial here to the same thing, 2x minus 3. Minus 3. Notice that we're getting the same kind of thing. Overall, in the long run, the graph is trying to look like 2x minus 3. But the closer we are to x equals c, the more the graph has to obey these asymptotes. It's like a gravity well going shooting along and pushing the graph away. Or we could think of it as the graph has to go around the asymptote. So if I, oops, that's not how to pause. This isn't YouTube. I can't pause on it. Also too far off. There we go. That'll do. We can think of the graph coming, you can't see what I'm pointing. I got to remember that people can't see what I point at. I can make obscene gestures and no one can know. But as the graph is heading up the line, it sees this asymptote coming up. It's like, oh no, here we go. I got to go around. So it just keeps going up. But fortunately, like asteroids, it goes off the top of the screen and then shows up at the bottom of the screen. Woo, warp. And then it comes back and then it can rejoin with that long run behavior of just the line. Note also, This is not just particular to polynomial functions. Here I have a function sine of x plus or minus 1 over x minus c cubed. So the graph is just going to look like sine of x. And when we're far away from c, 1 over x minus c, especially to the third power, is very small. But when we are close to the value of c, all of a sudden we get a vertical asymptote. And sine becomes irrelevant, being just something between -1 and 1. And it pales in comparison to this huge value of 1 over the cube of the difference of x and c. Any questions? How's everybody okay? Isn't it? It's like soothing. And you can do this multiple places and add more terms. Oh, maybe D is dots and orange. There we go. So it's like these rational terms, our vertical asymptotes, are like warping the function at a particular spot, like a little gravity well. Only instead of drawing stuff to it, it's pushing stuff away towards infinity. Any questions? How's everybody okay? Now we can really mess with things. Now I'm altering the amplitude. Oh, there, now the amplitude is being altered at the same time. Now I'm just being ridiculous. I like because it crosses over at 0 and the reflection has to go the other direction. So, except for that part where it gets super compressed and then it switches sides. I know it looks like it's smashing in and then smashing out. It's actually compressing and going all the way through. Because when D is negative, we're getting that reflection. Sine will reflect. Now, if I change the sine to a cosine, cosine is an even function. So even though it does reflect, we won't be able to see it reflecting because cosine is even. But sine is an odd function, not in that it's unusual, it's that its parity is odd. And so that's why we could change it from here's a positive sign and there's a negative sign. Any questions? Comments? Isn't it relaxing? This is what white noise looks like in my head. This is why I don't find it as relaxing as I probably should. So I imagine, oh, what if I change the sign there? So this came up because last week we talked about that function, which was really just an x squared plus 1 over x function. It had these two distinct parts. And we never really looked at the graph. We spent a lot of time looking at graphs of functions, and all of a sudden I didn't look at the graph of the function. And I really wanted to think about the graph of this function. How we could think of the x squared plus 1 over x. The x squared is what the function wants to look like, but that 1 over x is messing things up when we're close to 0. When we're close to 0, that 1 over x term is like getting in the way and putting a vertical asymptote. So really, when we wanted to draw, if we want to draw the graph, the 1 over x says a vertical asymptote at 0. And this long run behavior of, oops, I didn't draw a very symmetric parabola. Another way we could think of it is we could think of the graph of 1 over x, which has that negative leg and that positive leg, and we're just taking the ends and bending them up to our parabola. So instead of just having a 1 over x leg down here and a 1 over x leg up here, it gets bent into, oh, it was green in the demonstration. So it gets bent into this parabola. So instead of having a horizontal asymptote, like we would have if we had 0 plus 1 over x, instead of having that horizontal line at 0, we'll have this parabola. Close to the parabola, but as we get closer, then it has to bend away. So we could think of it as a 1 over x where we bend the horizontal asymptotes up into a parabola, or we could think of it as a parabola that where we have to slice it with this vertical asymptote. Yes. Yes. Like here? From on the right side, what is it? I'm not sure I can see what you're thinking. Uh-huh. It would depend on the values here, because what we're doing is we're taking this, the dotted line, the parabola, that's x squared, and then we're adding something to it. That's why we see the graph of x squared plus 1 over x above, because we're adding something to it. Because 1 over x will be positive on this side of x of 0 when x is positive. And that's why I drew the underneath the parabola when x is negative, because the 1 over x will also be negative, and so we're subtracting from the parabola. The amount that we're subtracting is very small when we're far away from 0, but grows as we get closer to 0. So depending on how much we're adding with the 1 over x, that'll determine how close this bottom part, the point that we were looking for, gets towards 0. So here we had 500 over x, or in this case r, and so it was at 3. But if we increase the amount that we're adding, then that will, if like instead of 500 it was 1,000, it would move it higher up. It would change how much we're adding. So it will move that point. And we were seeing that a little bit in the graph demonstration as the asymptote moved back and forth. Any questions? Is everybody okay? All right. So I thought about that immediately after, and I'm kind of surprised that I remembered that I wanted to talk about that today, because I thought, oh, I should talk about rational functions and asymptotes and stuff on Monday. But I had that thought on Friday, and there's usually like no way. I walk in on Monday, I'm like, oh, I don't remember anything that happened last week, and I just pick something new and talk about that. So here, amazingly, I remembered that I wanted to talk about this. All right, I hope that clarifies some things about rational functions and asymptotes and graph holes. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. You too.